In this video, we're going to discuss CRA models for integer exponents. So first, just to go over our exponents. So this is a to the x power. So a is our base number, and x is our exponent. How we want to interpret this is that if we see this format, this a some number to an exponent, this means that we're going to multiply the number 1 by that number a x times. So for example, if we see 3 to the 4th power, how we want to interpret this is 1 times 3 on 4 different occasions. So 1 times 3, that's 1 time, 2nd time, 3rd time, and then 4th time. Okay. So we're going to go over integer exponents. So integer exponents just means that our x here, that exponent, will be either a whole number or the opposite of a whole number, but we won't have any fractions or decimals, no rational exponents yet. The first case that we're going to look at is 3 to the 2nd power, or 3 squared. Okay. So again, how we want to interpret this is we're going to multiply 1 by 3 2 times. Especially with exponents like squared and cubed, we can also make connections between kind of to geometric models. So for 3 squared, another way you can think of that is, what is the area of a square with side lengths of 3? Okay. But we'll just kind of start with this interpretation. So this cube is representing that number 1. So we want to multiply that by 3. Okay. So you can think of that as 1 group of 3, 3 groups of 1. All right. So we multiply this by 3. So now we have a total of 3. And then that entire quantity, we want to multiply that by 3. So this is 1 group. We want 3 groups of that. And so the second, and then a third. Okay, so then we're looking at how many cubes do we have in total. So 3 squared, 1 times 3 times 3 will be equal to 9. Okay, and again, kind of going back to that geometric model, you can see with the square, these are easier to model with the geometric version. But you can see we have side lengths of 3, so we're looking at what is the area of the square. Okay, so that's kind of a common interpretation for the representational model. Right, if we have an area model of 3, then we're looking at what is our area, okay, which would be 9. Okay. And then this will just be the abstract model, kind of the expanded form. But this 1 in there will be kind of an important thing to keep in mind as we get to some of the more complex cases. Okay. So that was 3 squared. The next example we'll look at will be 3 cubed. Okay, so again, how we want to interpret this is we're multiplying 1 by 3 3 times. So 1 times 3 times 3 times 3. Okay, so again, this is 1. Right, this we multiply it by 3. Our first 3, so 1 times 3. So instead of just having the 1 group, we'll have 3 groups. Okay, so that's our first one. So we want to multiply this entire model by 3, so we want 3 copies of this as well. Okay, so we'll add 3 more. Okay, so this is 1 times 3, and then times 3. We still have 1 more 3 to go, so this is 1 kind of layer. We want 3 layers. Okay, so this is kind of, again, if we're thinking of this from a geometry perspective, this is kind of that volume model that isn't used a whole lot. Okay, so from that geometry perspective, then we're trying to think of, I'll try to turn this without ruining the whole thing. Well, I'm not going to be able to turn it, but we have 3 copies in there, 3 layers of 9. So we have a total of 27 cubes that are in here. But from that geometry perspective, then we're thinking of if we have a cube, right, 3 cubed, if we have a cube with side lengths of 3, right, this length and then width are 3, and then the height is also 3. What is the volume of our cube? So our volume is 27. There's 27 of these cubes involved. Right? So then for representational model, again, this is kind of going on the geometry one. Okay, so this is, then we have a height of 3, width of 3, and then a depth of 3. And if we want, we can draw in. Got some of these break lines here. Right, so we have a layer of 9 there, another layer of 9, and another layer of 9. Okay, so that's our example, concrete. And then obviously this is our abstract, kind of that expanded form for 3 cubed. Okay, we'll look at one negative exponent and kind of relate that to our definition here. So we're going to switch over to a fraction model. I'll kind of explain why. But so again, how we conceptualized this was we're taking the number 1, we're multiplying that by 3, but here it's the opposite of 1 time. Right? So what is the opposite of multiplying by 3 once? The opposite of multiplying by 3 is going to be the opposite operation, or dividing by 3 one time. Okay. So again, where that division comes in instead of multiplication is this negative side. So for our negative exponents, we went with the opposite of multiplication. If this was 3 to the first power, we'd do 1 times 3 one time. But here we want to multiply by 3, the opposite of 1 time. So we want to do the opposite of multiplication, which is dividing by 3 one time. Okay. So kind of our model for this, here we just have 1 circle, so that's going to represent 1. This is our 1. We want to divide that by 3. So divide it into 3 equal parts, and I'll stack this on here just so we can see it's the same size first, and then spread them out. Alright, so we're going to divide that into these 3 equal parts. Okay, so that's dividing by 3. So here I'm dividing, I'm kind of thinking of that as the number of groups, so dividing this into 3 groups. So then what is the size of one of these groups? One of these orange pieces is one of the 3 equal parts that would make up this whole 1. So one of these pieces is 1/3 of this original 1. Okay. And then representational model would be right similar. If we have 1, I'm going to divide that by 3. Trying to get decent thirds here. The drawing is a little tough. Okay, so then we're looking at what is the size of each of those 3 groups. It'd be 1/3 of the whole. And then our last case here is going to be an exponent of 0, right? 0 is an integer as well. So again, how we're interpreting this, right? So we're starting with 1, we're going to multiply that by 3 0 times. Okay, which means that we're not going to multiply it by anything, right? If I'm going to multiply by 3 0 times, that's already been done. I've multiplied by 3 0 times right here because I'm not going to multiply it by 3. So that's why these exponents are going to be, these zero exponents, all of them are going to be 1. Right? So we're starting with 1. The models for these are not going to be very exciting. Starting with 1, multiply that by 3 times, so we want, right, if we're going to multiply it by 3 once, we would have 3 more copies, but since we're not multiplying it, it's just going to stay as is, so it will stay as 1. Okay. Yeah, so those are the, obviously modeling some of the larger exponents, right, like 3 to the 7th power. Hopefully by then we'd probably want to start with the models when we're introducing these. And then by the time we get to larger exponents, and not need to rely on the models and go in the abstract. But again, kind of what can help with modeling, especially when you get to the zero exponents and the negative exponents, is this definition of multiplying 1 by that base number, the exponent number of times, because that helps with that negative, understanding that as division, since we're doing the opposite of multiplication.